all of you at this very wonderful event, the joint seminar of TÜBİTAK Research Institute for Fundamental Sciences and TÜBİTAK Marmaris Research Center, which will organize basically rely on the unifying feature of science for humanity, which provide us with the power of sharing ideas and understanding. As you know, recent advances in electron microscopy instrumentation and methods have made it great progress in physical and life sciences. This in turn makes possible identifying and challenging addressing new fields in this area. With this in mind, it is our distinct pleasure that we have very special speaker, a world-class expert in the field, as well as a wonderful person, Professor Xiaoqing from the University of California, Irvine. He is going to give a great talk on probing the emergent properties and dynamics of interfaces by electron microscopy. At this point, I want to hand over the word to the Vice President of Marmara Research Center, Dr. Osman Okur, who will introduce our speaker. Please.
Is also natural direct voltage surviving material surface to transport type of transport context whatever. The second is an intermediate to recognize metal samples have become multiple is final development and verification of normal transmission electron microscopy methods for polling according to the proposed survival behavior of material. This works has led to discoveries of new material and power functions. Second, the system is a generator and times the assumption is level. These are electric thermal server protection, electron particle society, microscope society, and material research society. This published over 400 years paper in high service. I want to thank the for the last system and invite for the response.
Thank you, Vice President, Dr. Ali, Director Ali. Ladies and gentlemen, good morning. It's my pleasure to have this great opportunity to present our recent work on electron microscopy. This is a new work for me. First time to visit Turkey, although I have friends who worked in Turkey for a number of years, but just hard to manage to get here to visit. So finally, I'm here. And although we have suffered 3 years pandemic, but now fortunately we are able to have interaction in person. So it's my pleasure to be here and to meet all of you. If you are interested to talk about science, after this seminar about the next 2 days. And there are the schedule, so just very good for interest in science. All right, so my presentation is entitled Probing Emerging Properties and Dynamics of Interface by Electron Microscopy. So I first tell where I come from and what is my research interest, and then move on to the specific topic for today's seminar. This is a map of Southern California. UC Irvine is located between San Diego and UCLA. It's closer to the UCLA airport along the west coast. Irvine is a new city, it's a French, and it's about 7 age of the university, so about 55 years old. And it's one of the 10 UC campus. But you see, each campus operates as independent universities. The University of California, Irvine has is built around this central park. So this quarter is for engineering, that quarter is for science. My appointment is between engineering and science. So I work for interdisciplinary institute called Irvine Material Research Institute, was established along with my move to UC Irvine. So that was part of my job, establish this institute. We use a first of all these recorded fields which are stable for electron microscopy. Irvine Material Research Institute. The Irvine Material Research Institute consists of a state-of-art material characterization facility, particularly for atomic resolution characterization of materials, the structure, composition, and properties. This is the initiative started from university, and then with a recruiting of the center director, and that was me, ended up with me. And then established this material characterization facility with a whole different facilities organized as an institute. With a common structural analysis for X-ray and other things, and then surface science and transmission electron microscopy, which is completely new since last 5 or 6 years. We also have a new facilities for material characterization, particularly for soft materials and small instrumentation, but organized and accessible by all individuals, both for university or also. And then future expanding to quantum materials and energy materials research facilities. This is basically how the facility is being organized. So the facility is organized as a shared facility for all the researchers in material science and engineering, also biological science. And we have 8 PhD level staff scientists who are very well trained experts in each of their expertise area, and also have training staff. We have some unique facility for atomic resolution TM. I will show you through my detailed work to see how the unique functionality of obtained for this instrumentation. And then this facility is available to everyone who are interested, not only just from UC Irvine, but you see UC Irvine typically we use about 60 to 65% of the TM part, and then other universities around it will use another about 20%, and then about 15% for companies, 10 to 15% for companies. So this is a great resource. The research facility is one part of the Emergent. So another goal of the institute is to establish center of excellence. We are fortunately, through the last few years, we obtained a National Science Foundation's Materials Research Science Engineering Center, which is called MERSEC, which is very competitive to the US, and major universities in the US try to get this center. So we are fortunate to get this center for the first time in the university history. And we got the center with a 2 focus research area, one is the complex concentrated materials, both including metal and ceramic materials. Another is bio-inspired active materials, which is involve chemists, physicists, and chemical engineer, and they study the supermolecular materials, which can be tuned to become interface between bio and real materials. So this is a 2 different focus. And this center involved 18 professors, 17 from UC Irvine and 2 from outside collaborate. They have to work together collaboratively for each these individual 2 topics. So they have to collaborate, and this in the same way. So the measure of the center very straightforward. So people either collaborative and then publish together as co-authors. If you just do a great job, a great work, and just involve in the whole group, and then it's not success. So this is a mechanism for the analysis muscle. But there is an overall picture about carbon material resilience to, and also how this was organized. The presentation is more focused on the work that have been done in my own research group in the last few years, particularly for advancement of electron microscopy. The materials studied in my group mostly is thin films and nanostructures built by layer and the actual growth method. So my group we have the atomic layer actually by post-layer adaptation, and then we control the growth. But we also collaborate with other MD group and getting this nanostructures materials by thin film growth. So there's only slides I talk about synthesis. So by focus of the presentation grouping on the atomic scale and the study of the structure of the relationships, particularly in the nanostructure and the surfaces. So in my group, we are focusing on the probing atomic scale structure property and dynamics of interfaces, particularly in the nanostructures. And the science we are interested in including emerging interfacial phenomena such as atomic scale structure, property, dynamic behaviors, and also the structure property relationship. This is important to understand the processing and design of the materials, and also how to counter real functionality of the materials. The materials that of our interest, including quantum materials, particularly for strongly correlated materials, ferroelectric and multi-priority materials, and recently a lot of interest in 2D materials. And that also interested in the energy materials, including single atom catalysts and photovoltaic and batteries. And you will see there's a very important tools for electron microscopy allow us to study the functionality and also the structure and chemistry of the materials. It was an institute here. You see how the structure, microstructure, composition change topology, and even atomic scale phenomena can be understood with the in situ method. I will show you some example. And this is a new development will be expanded with So now I just focus on more specific topic. First, on the very quickly introduce ferroelectric material. Ferroelectric material is characterized the existence of spontaneous correlation, and which can be switched back and forth by applied electric field. And people know the magnetic material has very close similarity. And ferroelectric, due to this switchable functionality, ferroelectric material can be used as memory devices, which is already a commercial product. This is a one example showing Nuhbalaoğlu crystal, but still have a process structure. And this crystal is distorted from the body diagonal direction, so that the correlation between material become polar. This is showing unit cell symmetry. Can be pulled along one of the body diagonal direction, and this will generate different kind of domain structure. Overall, the cross-cut material, that it will in the cross-cut material, you can see three different kind of domain structures with a correlation changing directly by 180 degrees. That's like an interface on the steel ferroelectric domain wall. This is a 109 degree polarizing rotation. This is called 109 degree domain wall, or 71 degree change of the polarization direction. This is called 71 degree domain wall. So overall, with this kind of material, you have a three different kind of domain wall type. And this domain wall motion dynamics will determine the property and functionality of the ferroelectric material. This is just the TF image showing how the domain structure looks like in the TM. You see the plan view TM study, you just electron beam delivered to this surface, and then all this domain wall will appear as a stripe, this along parallel along the beam direction. And then if you cut the material in this direction, And then electron in traveling on this direction, and then you can see the structure looks like this, and exactly just like that here. So this is a cross section of the same sample, because now it gets 3D view of the domain structure in the ferroelectric material. So in ferroelectric material, although it is it has to be used in the memory device and many other kind of devices like actuators and sensors and so on, but still have a lot of unknown, unknown phenomena, and also some scientific question, fundamental scientific question was is not answered. So this including the origin of electricity and how the domain can be reflected and grow, the interaction between the moving domain wall and crystalline defects, interface, and so on. And also the electrochemical condition and boundary condition is critical for the property of ferroelectric material. You know, all this to answer those kind of questions and require a quantitative resolution imaging of the domain walls and domain engaging process, and to see how they are going to measure and map the spatial distribution of the domains and domain wall, and also the normal states of the polarization. If you change local boundary condition, the polarization state will change. These are new fields need to be explored. The exploration of the atomic scale property of ferroelectric has been going on for decades. I just want to highlight a few things that we did earlier when I was vision. So that time, and then the atomic scale measurement of polarization is not available. So we developed that using quantitative TM methods. At that time, there's no emerging TM, but we can use a quantitative method involve atomic structure simulation, image simulation, and then to model the system, and then get precise position of each element in the crystalline materials using the coordinates determined by quantitative TM. And then we can determine the center of the positive charge and center of negative charge, and then we will know the type of movement for when units, and that this is the way to determine the polarization and by determining the type of movement from unit cell to unit cell. This was done by early and this is about around 2000 to 2002, and then the next generation student Chris Nelson, and he further developed this method by using operating current TM. This the TM used was the very powerful TBAE microscope located in Irvine National Lab. And this was a US Department of Energy graduate program. So we start very stable high resolution microscope at that time, using the technique developed by WK. And Chris was able to develop a tool to automatically map the type of movement from unit cell to unit cell, so that you can use this method to discover the unknown phenomenon. This is just a cross-section TM image of ferroelectric. This was polarized, going on the turbine standard, which is an insulator but has similar crystalline structure as a EFO. So this interface is covariant. So the ferroelectric will insulate, they have a multiple domain structure. Then the combination of the domain, this straight boundary is a domain wall. The polarization will change from here to here to here. It just change by 190-degree rotation. But you can see that it's a very interesting phenomenon. If you look at this domain wall today, it's very straight, nothing special. But this domain wall is straight, and then you have this dark region, bright dark region. This is a triangle like here. Now you look at along this straight terminating triangle domain, straight terminating triangle domain, and there's no exception. Then it's in our eyes, and you know this is looks. There must be something wrong in physics to try to understand this. Now, if you look at this small region, including two perpendicular vertical domains combination, one with defect, one without defect, and then enlarge this, just with the high magnification, you see a atomic resolution image from the region. just look at it, you don't see much. But if you use the method developed by Chris and William, you can see the dipole moment from each unit cell. Now you see the polarization is changing from this direction to that direction. It's not a vertical, like a 90-degree rotation. But remember, polarization is not exactly in plane. It's about 45 degrees away. So the angle in 3 dimensions is 109 degrees. So this is 109 degree moment wall. And this part set just up and down, right? This and that 2 domain wall just very similar. Both are 109, just the opposite rotation. But this here, this reading is quite interesting. It's polarization, you follow the arrow. Go up, gradually turn, and then to down, and then to the left. This is called closure of phase. This also the similar pattern exists in magnetic system. But what is the reason for this? And then very straightforward from simple physics perspective, we can and get this kind of picture. So polarization, the paradoxical material is, we have a bond charge. So it's start with negative charge, positive charge with other hand, and then line up. So when this moment accumulate at the surface or interface, you have a negative charge on this side, positive charge on the top side. So this charge is called bond charge. So it doesn't move itself, it's appended to the structure. And then the polarization is pointing downward. You have a positive charge here, negative charge there. But if you look at this accumulating point of the domain wall, this one and now, then you see interesting thing happen. This bond charge at the surface and change the sign at the terminating point of this domain wall. And then there's an internal field created by this bond charge that is pointing to the left. But this side is pointing to the right. And then this internal field will influence the orientation of the dipole moment in each unit cell. So that means the field is parallel to the projection of dipole moment that's called along the left. But here, the projection of dipole moment is pointing to the left, but the bond charge induced field is pointing to the right. Therefore, these dipole moments will not be very stable if this field exists. Therefore, it will change its orientation very from very interesting closure objects. So this is the origin. And after this was observed, many people in the parallel research field are interested to create, manipulate this kind of closure problems. This is 2 examples. One is from Institute, Material Research Institute in Chinese Academy of Science. And they found this kind of vortex, anti-vortices in the circularities of strongly partnered and negative partnered. So this is very similar to the closure problem we've seen before. And also, my student Chris Nelson, when he finished, he developed this method for mapping, and then joined Berkeley for school, and then continued to study and found this very nice vortex, antibodies. And bodies, antibodies already in the very hard thin layer with the circularities to the structure part. You just be not in the same. Well, after this, there's a lot of colors, spherules, and edge of domains, and we can kind of narrow structure, narrow scale polar states was discovered. This topic actually today is very active, so far. The narrow scale polar regions, polar states, or ecological state, in parallaxic bodies. So far, I expect what happened in the atomic scale and keenly determine the polarization in the nanoscale, in the unit cell scale, and how to map the polarization change to the 3 dimension, and then this will now provide a way to discuss nanoscale phenomena such as global domains, voltage, antibodies, arrays, and so on. And another question I mentioned earlier, and how the paraelectric domains nucleate we apply electric field or change apply a driving force. And what is the dynamics? This question is very interesting and raised several decades ago. When I was in graduate school, you see right there, you can guess how long it passed. So this is my master thesis, and study the paradigm field, and see the paradigm of minerals. I think this is the first direct population of paradigm of minerals. Most exciting is that every form of mineral terminates at one point from a vortices. Okay, and then this structure will change with heating the sample to the transition temperature. And then after I moved to Germany for continuing my PhD thesis, and then working on another parametric material, which is a dancing green chloride with a Professor Xiaoqing. And then you can see that there's a two domain wall and which are very close to each other from pair. And then these three pairs can join together from vortices. These vortices will change its configuration when you change the temperature. Change the temperature, you have a temperature gradient. Temperature gradient is driving force that push the middle wall and vortices move. And then this is the reason why I sent from my computer, because this video doesn't play. If you play these triangle domains, will move the vortices, will move from here to here when the temperature getting higher and higher. Okay, so that was another. Yeah, another video is not the video. So and then my professor asked me, just like a ferromagnetic field, if you apply a magnetic field and then you can speak the wind or move, you do the ferrite. This was great, question was great 35 years ago, 30 years ago. So and then I said, well, maybe, but we tried, but you see that 30 years ago, the technique is not advanced. It's very hard to do this. So it was not possible. Right, all right. So and then I keep this in mind when I become professor at Michigan and still want to solve this problem. And then one of the graduate students was committed, Chris Nelson. We started with a conventional prototype, the scanning block in the TM, and then by bias. And then the system looks good and promising, but it's really not designed for this type of work. And then you have the development technique, and then just brought a lot of components we designed. This we make a new product, which has become very stable, and this is new product. And then which allow you to apply bias from to the point of interest. And then you can see atomic scale action. Because of the video are not used directly, cannot see motion. But basically, this code will allow you to apply electric fields locally, and then you can see the atomic scale motion is very stable within the atomic energy. You can also measure the local electrical property, like a CV IV code from local region that you are interested in. Then you see this can be measured directly. These become quite useful. Thank you very much. So, okay, now this is good. You see, this is the first in situ switching of parametric materials. This is a STM tip. This is the photoreactors. It's also oxide. structurally match very well with substrate and the ferroelectric heat. So you can see that when the electric fields applied up, positive and down, negative, up and down. You can see the equation starts from the here, the field is strongest, and then might propagate further. And then this is like how the memory device, ferroelectric memory device works. Okay, by checking the volume of the new domain switch, you can see the ferroelectric hysteresis loop can be obtained with the integer video here. And then with the atomic resolution imaging, you can determine polarization, and you can see which are the domains nucleating. And most importantly, when the domain nucleated here, and the domain, when this dark reading starts to extend, that means the domain wall is moving. And they can track it. There's a dark point here, that is a dislocation. You can see how the dislocation affects the motion of the domain wall. That can be explained here. So this is dislocation, the domain nucleated, the domain wall moving to here. You can see a little slow down here, but we need to analyze to get information. So then you can track how the domains move to the vertical direction, that is velocity measured here, or the domain wall, the motion along the horizontal direction, the velocity is tracked here. You can see that domain wall motion, getting slower and slower because the field is getting it's moving away from the strong field region, and then slow down. And then eventually, it is almost not moving for a while. And then suddenly become very high speed again. The reason for this is that the domain move to here, domain wall move to here, this dislocation, holding the domain wall, and it will just like a barrier. And then when the electric field increase further, the driving force becomes higher and higher. Eventually, the peeling effect of dislocation will disappear, overcome the barrier, and then move further, and suddenly move very fast, and then slow down. So this is the first demonstration of the peeling and peeling of dislocated domain wall by defects. All right. So that demonstrates dynamics can be studied in the in-situ electron microscopy. And in ferroelectric material, because it's similar to ferromagnetic material, you always, if there's a no charge balance, and then the ferroelectric material will try to break down to form multiple domain structures like this. But if you look at the termination, as I mentioned in the previous example, bond charge. The bond charge at the interface with insulator will be very important because the bond charge has increased energy. With the system, have some free carrier, and then the free carrier with opposite side of charge will be trapped at the interface. And then the trapped charge cannot leave from interface, but can move around the interface. This will form the two-dimensional carriers gas. If electrons trapped to compensate the bond charge, positive bond charge, you have a 2D electron gas. If holes trapped to compensate the negative bond charge, you have a whole gas. This is just theory, just by looking at the interface. And this is also predicted by a theoretical calculation. But for a long time, there's no direct measurement. Measurement was available, but it's also insulated that no electron gas in ferroelectric interface at all. So what is this? Why? Now how can we understand this? So this is our in-situ experiment and show the sign to the new interface between ferroelectric and insulator is conducted. So this is a very well known about previous example, right? Switching this is like a very small tip. The field is strong here, and then first nucleate and then more further. It's a rejection only. And then this is another sample, very similar to the first one. You have an insulator. This is a 2-dimensional other conducting outside of the bottom electrode. This is ferroelectric. This is another insulator, the strong positive. So this structure is similar to that, except a additional thin STO. And then you apply electric field on the top of the STO across this PZT. And then you see the important things happen. When the electric field increase, nothing happens. Still have a monodomain, single monodomain structure. When the field increase further, then you see this region will switch along the whole film and suddenly become bright. You'll see that in a second. I think it is there. You saw that happen.
Yeah.
So and then these things we just worried if I do it again. So okay, so this is switching at one time, just like a capacitor. This means that there's a bottom electrode to reveal, and then it must be a top electrode, but we did not intentionally make top electrode because STO is supposed to be insulated. This indicates that either STO is conductive or the STO ferroelectric interface is conductive. To rule out STO is conduction itself is conductive. We just prove different STO layer with different thickness. If the conductivity is switchable, it is a scalable, and then STO is conductive. So we did that. We have many different STO thickness and always the same conductivity, so not scalable. And then the concluding interface is conductive. That's good. Okay. But we further ask question, if the electrical carrier at this conductive interface is a ferromagnetic order or not. And then we design a few experiments with under refraction spectroscopy. We determine the interface is conducting and also ferromagnetic order. And another signal is a high resolution remote experiment. Also confirm interfaces conducting the carrier is magnetic order. So that means we have two electron gas with a magnetic order. So it's a spin polarized electron gas at interface. But the question is why so many studies in the ferroelectric have structure already show that the interface between ferroelectric and insulated is insulated. The reason is that the film that our bulk material people measure always include different kind of domain walls. So for this kind of domain wall, you have a conducting electron gas. But then if you have a 90-degree domain wall, the correlation is a parallel to the interface. There's no bound charge at interface or surface. Therefore, there's no two electron gas or 2D4 gas exists. And then if you have correlation up and down, and then at the bottom or at interface, you've got electron gas and cool gas alternating. And the junction from PN junction now block the current. Therefore, the microscopic measurement of ferroelectric material interface that's always shows insulated, not conductive. So that was under the question. And then we did a similar study on another ferroelectric material. My student, he was trained in TM, and he was also interested in the very interesting capacity of scanning flow. You can do piezo force imaging to see the domain structure. You can do conducting element study to measure the conductivity at interface directly. He said, I can study the same sample with my cross-sectioning TM, and then use a cross-sectioning TM sample to measure the functionality. I thought that was difficult, but he managed to be able to do this. You want to quickly introduce the data. That's really exciting. So this is a physical chloride ferroelectric going on 13 standards with the derivative substrate insulator. And then the interface you can see is a very conductive. This is a high intensity. Dark is high intensity conductive. And then the conductivity also changes from one domain to another domain. You can see it's alternating. And then this is shown by the profile, the line profile. So why the conductivity? Conducting is okay. From physics example, we understand the ferroelectric interface can be conductive. But alternating is also understandable by PN junction. So when the polarization is pointing downwards, and then you have an electron gas, and then pointing outwards, then you have a hole gas. And then there's a whole electron conducting region connect to each other. You will form PN junction alternate one to another. So this will be the display here. So physics behind this. We have an Afghani symbol from the University of Nebraska. He was the person with the first principle calculation predicted the ferroelectric insulated interface is conducted either from two electron gas or to the whole gas. But other microscopic measurement is against that. Okay, and then we talk about our data to feel really excited, and then you do an additional calculation. And you say fill the soup cells and with the different thickness of ferroelectric business product. The conclusion is that the ferroelectric business product is thicker than 8 millicells. And then the band bending at interface will make the interface either p-type or n-type. And then electrons or hole will be trapped. This will depend on polarization pointing toward interface or away from interface. Okay, this will from alternating in A conducting material. This explains why we measure the conductivity across the domain stripe is insulated because they're just series convection. But we measure along the stripe, it is all conductive. So that was very interesting on observe. So this is just summarize the conductivity of two different kinds of ferroelectric interfaces. Explain why in the microscope measurement insulating, but in the nano scale it is conductive. Okay. So this give you address another question. Yes, so the charge at interface is very important to directly see this kind of electronic charge at interface. And also in the polarization measurement, the quantitative method that we developed to measure the dipole moment from unicell to unicell, we only use ionic displacement because we have not yet considered atomic the electronic charge. So the polarization referred to should consist of both ionic displacement and also electronic displacement. Any neutral atoms put in the electric field will have induced electrical polarization, electronic polarization. So they should be considered. So to do this, we have to measure the local electric field, right? Including both ionic and electronic. So can we image the total electrical charge density? Actually, experimental technique is there, but not for atomic resolution. X-ray method is very well, but it is a macroscopic sample average. Electron beam, converging beam electron refraction has been developed for decades, and they also offer the technique to measure, to determine charge density, but use the fitting of structure effect that can get very nice as the measurement of the polarization of the dense charge density. But it's again, this is a space average that depends on how big the crop size is. For this kind of CBD, and then the crop size typically the huge size now, not with the atomic scale. Right. So that was motivation for us developing the charge density map in the interface local structures. We were stimulated by Clue's theories. It was very simple, straightforward way to explain electron beam crystal materials interaction. So the electron pass through focused electron beam pass through the specimen, and then specimen electron beam will lost some will change momentum. The momentum change is directly linked with the crystal field. Electron pass through the specimen. The local field is proportional to the change in the momentum. So with this, we did expect that when electron drop and is passed through the sample, will sense the nuclear charge, and this field due to the charge is to the left, and then the electron diffraction pattern, the center of the mass of the diffraction pattern will move to the right because of attraction. If you move the beam from left side to the right side, and then this displacement of the center mass will be opposite. So this is just perspective, right? So in order to do this, and then we'll do simulation and see if this is true. So this is a Chris Ediago, PhD student, calculation, and then simulate the fact that converging the electron destruction pattern when the beam is scanning through the crystalline material very slowly. So each point is a well-defined pattern. We call this as a 4D scan because the 4D two-dimensional scan, you have a 2D data. Each standpoint, you have a one diffraction pattern that is also 2D data. So total is a 4D, we call 4D stack. So with the simulated diffraction pattern in 4D, and then you can calculate the chart, the field. The field is proportional to the momentum change. And momentum is determined by the center of mass displacement. Okay. So this electric field from the 4D stand, you can see that for strontium tartanate, you have a cubic symmetry. It's all like a radial symmetry. That's good. With this field determined, and then you can get in chart information. That will just come into on the next slide. But there's a question: in which kind of scenario this interpretation will be valid? In other words, what is the limitation of linearity? So we did a detailed analysis. It turns out when the sample is big enough, for this particular example, sample has to be 5 nanometer or thinner near the linearity. So I'm just not with the detail. So that we know when these methods will be valid. So with electric field determined, and then you can using the Gauss law and then to determine the chart. I will show you in the future slide. So the way this is, tell you how the 4D stem can be done. This is a movie done by Colin. This is directly simply showing you how 4D stem will work. The electron beam will scan through the specimen, and then will at each standpoint, you get a diffraction pattern. This is a converging diffraction pattern. You collect this data. This is a 4D data, right? And then you analyze this data. You will be able to get the momentum changes, and then get the electric field. So there's the method is now we think quite confident may work. Now we want to experiment. This is a 4D data. For each data diffraction pattern, we just calculate totally exactly. This is similar to those people who RT and Acosta, this is a hot image, right? But the 4D data we have, at each data point is a diffraction pattern. We will analyze the center of the mass displacement. We'll get field. This is the field. With the field, and then we can determine charge distribution. So this divergence of the field, you'll get charge. This is actual charge distribution. This charge is total charge, electronic charge, and also nuclear charge. And this will determine the local potential in the first slide here. All right. With this method, we demonstrate the charge density method for 2 different materials. One is strontium tartanate, which is a prototype for the outside. A similar structure, but different kind of paraelectric property. This is no paraelectric. It's a symmetric. This is no surprising, very nice symmetric field distribution. But for paraelectric, bismuth fluoride, the polarity, as I mentioned earlier, polarity is around body diagonal direction. You can see that this polarity is very clearly demonstrated in the field method. Now, if you go further, divergence of field chart tell you the charge density. This is the charge density of strontium tartanate. You can see the electrons, which is a negative charge with a red color, is uniformly around each atomic column. So this is good. This is a pure crystal. But for the paraelectric, which is polarized, so now you can see the electron charge is no longer uniform around the column. And then it is on a bridge between ions. This is very important to form a bonding. And also, original paraelectricity in bismuth fluoride is related to bismuth, 6f electron. It's a non-pair. So this will give you a lot of information, but I'm not going to talk about that details, and still in the early stage. But let's just compare the experimentally obtained charge density in these two different materials. One is ferroelectric, another is not. With the first principle calculation things. DFT can also get charge density, and for both these two materials, you can see for strong time that match very well. For ferroelectric material, bismuth chloride, you can see it's quite similar, but there's some details are not exactly set. So which is correct? So actually, I don't know. So I asked my collaborator for the DFT expert. He said, I not tend to say DFT is more accurate because DFT potential still needs to be optimized. So that's why there's a lot of active work in machine learning optimization of the electrical potential. So we will answer this question later in the future. So, but this is very encouraging. So the density, charge density can be mapped by using experimental method. This applies to small nanostructures, also interfaces locally. So by knowing the charge density, and then you can use it to determine the center of negative charge, center of positive charge, and this including ionic and electronic contribution. With this, we can determine the dipole moment for each unit cell of this material. This match very well with the bulk value in the business problem. Okay. Now we have charge density distribution, and DFT people also calculate charge density distribution. From their data, they evaluate so-called the vector charge analysis. You can analyze using the charge density distribution to analyze many properties, including bounding characteristic and valence states of each individual element and so on. You can do the same for the experimental data. Just to use example, okay, this is one of the this also probably the same paper we have just as addition as an application example. We are strongly taught that it was integrated. Bismuth chloride is ferroelectric. And therefore, interface are very much can be with charge interface. This is the hot activity. This is the charge electric field. This is charge distribution. By analyzing charge distribution, we can directly see the existence of electron, two electron gas. Okay, because the polarization is pointing to the interface. And additional analysis by looking at the position of each airline's anions and also electronic charge distribution, you can see that the change of structure is much faster than change of the electric property. The polarization will penetrate to the non-ferroelectric material as to the but the structure distortion is quite sharp. It's only 2 unit cell or 3 unit cell thick, but the polarization and change will across about 5 or 6 unit cell double. So this is one example. So with the technique to develop, there can be many other things. Another big example is our very recent paper, and we use a 4D step to determine the charge distribution and field distribution around the polar spinning. And this is a very nice example to how the polar spinning looks like. And this polar spinning is switchable by applied electric field. If you are interested in this, then you check that. This is not the box of the talk. So this is a quick summary of what we see by in situ TM by 4D STEM. We can get the dynamic process, we study the dynamic phenomena, and also the local charge distribution and the understanding the electronic property of the nanoscale. But if I have 5 more minutes, I'll just touch another area I plan to talk about. So with electron microscopy technique, actually with advancement in electron microscopy, both for aberration corrector and monochromatometer, plus the direct electron detector today, we can have a high spectral resolution. We can have very small probe for the scanning transmitting electron microscope because scan. And we can also build improved energy the analyzer to analyze small energy change in the electron beam. So we use electron energy loss, such as Xiaoqing. With this, we can study the dynamics of lattice vibration or falling for the individual defects, which is not possible. But I'm just not going to cover the detail use this. I just want to mention that as the device in the electronic industry continually minimize until 2 nanometer scale, and then the local heating is important. And then another important is a thermal barrier coating. You know, when you don't want to heat transfer to the inside of the device, even for the engine, right? You will block it. So to understanding the heat transport in the interface is important. But the theory about the thermal transport are developed using computing theory. It doesn't work in analysis. And also people working on the thermoelectrics know that there's many engineering methods to improve the functionality of the thermoelectric fields by introduce interfaces scaffolds. By introducing nanostructures will have lattice effects, then also scaffold. Or atomic scale error. This is a multiple element to substitute the individual species. And then all these three different mechanisms, there are different mechanisms and it's supposed to scaffold in different ways. But this is all just from physics perspective. It's a theoretical study. But how do we know it follow scattering in this scale, and how heat is transported in this nano scale, in the atomic scale? Some experimental methods already show that when boundary conductivity in diamond is much lower than foam, right? So like this is a rule is low conductivity, no thermal conductivity at the boundary. Also at the interface, like silicon genetic interface, is a model system shows that the interface between silicon genetic scatter follows and then low conductivity, thermal conductivity, right? But there's no direct medicine, no or local medicine. So electron microscopy developed. In addition to image, you can also analyze the functionality by using EOS. So EOS can be done in different ways. So EOS scattered by the various electrons, the co-electrons that were in the ionization energy. You can study the existence of the element in the material without co-loss use. The electron can be scattered by various electrons, and then this will allow you to study the electronic property like a bandgap and any kind of related to the various electrons. Or electrons scattered by nuclei, and then nuclei vibration, that is like a vibration of lattice or photon. This involves very small energy change in the electron beam, but now with a new technique developed, there's a very small change, like a few milli-electron volts can be detected. Traditional TEM, they only detect energy change with 100 milli-electron volts or higher. These are monochromatic TEM. But there is a larger dedicated step, you can study very small energy change. So this is one of the instruments in our lab, which is quite unique. At 330 kV operating voltage, we can get a 4 milli energy resolution. This is a very important development. So with the EOS method, we can study the diffraction of electron in the scattering TEM. So with a large converging angle, all the diffraction bits are overlapped. There's no distinguishing between different angles. However, if you reduce the converging angle, you see many different spots. Each of these diffraction spots will tell you the scattering to the particular length. And then if you can analyze electrons scattered to different angles, and then you will see the angle result, the scattering of the electron beam by lattice vibration. In other words, you can measure dispersion curve that follow in the from local region. Okay, So this is just the drawing of the Fourier zone. There's a first Fourier zone, and then you have the other Fourier zone. But most important that if you have a large angle resolution, and then you can make many data points, and then to do the formal dispersion analysis similar to the future. So this is the example that showing Sonaka and he did idea work a few years ago. This is the structure collected use huge amount of time. Each structure will take about 10 to 20 milliseconds, and then this is millions of structure put together and take very long. But this is demonstrated principle. But now with the view detector, then use a much shorter time. With a direct electron detector with a 6 aperture, and they can get these, there's a few minutes, quite big improvement. On the demonstrated technique that we are further developed. So by using this EOS, vibrational EOS method, we can study the following characteristic at individual effect. This is just a single stacking fault in silicon carbide with 3 Cs, cubic silicon carbide. You see, this is one crystal, another crystal, you have one shape. This is stacking fault. By using the leading range converging angle, we get a standard solution. And then we study the function and the EOS spectrum from the interface, from the defect, and from both. You can see they are different. And it will be much easier to understand using imaging. You can see that this is the you take about 90-degree image this. So this is a position. This is a position. Here's the interface. Okay, the interface is here. It's taken for. Okay, and then this is an allergy. The color indicates the intensity, how many photons with a dark energy. Okay, you can see that at the second part, this TN mode is appear as a new mode. And then the existing TN mode, LN mode in the silicon carbide is significantly suppressed in this region and from the new mode. That means there's a new amount of new photon exists at the interface. That's a single stacking point. And then we also analyze details. What is energy shift and what is what. But to demonstrate the mechanism, I just want to use this theoretical observation by Professor Wu and build the model with a silicon carbide. This is a single stacking fault. You can see here atomic scattering in this stacking fault region. The amplitude, and also the angle of bounding are different from the bulk. And then there's a new mode at the stacking faults to form. And this new mode contributes to the EOS, the density states of phonon. That's why we see the new phonon modes and also the change of the phonon energy in the world across the interface. Right. That was a great example for the single clarity effect. What about the nanostructure? A typical nanostructure, if you choose an example, would be a quantum dot because it is very well engineered. And then we choose silicon generic single quantum dot. And then quantum dots shoot from superlattice, just a continuous chaotic flow. And then each quantum dot will just like a donut. Notice that there are two kind of interfaces along each quantum dot. The bottom interface is very sharp. It is constructed very sharp. The top interface is a glory, which is diffuse. The composition of silicon generic ratio is changing gradually across the interface, across this interface, but abruptly along that interface. This is demonstrated here. This also shows there's a new phonon mode and mode, the optical mode of silicon and have a chip. And this is similar to the silicon carbide. But most important, I will see that the energy shift of the anode mode is consistent with the change of silicon genetic ratio. That means if you change the chemistry, you change the energy of the phonon. Okay, that is straightforward because of that, right? Okay, that is not surprising. So what is surprised us is that the phonon population indicated by the density of the yield structure. So the phonon population you see from this is a profile across the phonon belt. So this is a wet interface. This is another interface. This shows a little bit enhancement at this interface. That's top, diffuse interface, a little bit enhancement, but huge enhancement at this interface. So we try to understand why. That means you have more phonons on the side of each interface. But the enhancement at different degree with the two different part of interface. So we try to understand this, and then we think about very simple model. Electrons will be able to measure phonons, but electron is high energy, which is also be able to create phonons because there's a feelings lose some energy to magnetics and they generate new vibration. So if a vibrational wave generated in a crystal sampling study, and then you have two quantum dots beside it, and then this vibrational wave will reflect upward, and then see this direct sharp interface. And then this sharp interface is get electrons and then coherent, and then a more wave the constant effect of refraction, like a spectacular refraction. This is a diffuse interface. It's not like work as like a mirror. Still have a bit of refraction, but not very strong. It's more diffuse spectrum. Therefore, some phonons still affect on spec, but to this extent. But therefore, the phonon population here will be higher than the background. Here also much higher than the background. Therefore, this explains why we have two different enhancement. In other words, phonon will be scattered by interface depending on the sharpness composition of the interface. Okay, this was a good idea. We think about the interface data. We will talk this to the expert of nano thermal transport, Professor John Chen at Penn State. He's a leader of this nanoscale transport research. And then he built the models and then to see whether or not to get the result for simulation. It turns out that worked very well with our intuitive model, and then to support the refraction of phonon depending on the sharpness and composition of the interface. And that is great. Now, if this is true by model, but can we directly measure the direction of phonon propagation? In other words, can we measure the momentum direction of the phonon? So this is another method we developed in this work, and probably the same paper. So we just measure a phonon with two different kind of cube, the momentum of phonon. One is a plug, another is a magnet. And then have a two map of 10 and then subtract from each other. This is called differential mapping. The differential mapping will tell you what is the net direction of phonon change, right? Phonon can go this way or down. But net, this differential value will tell you how many net phonons could get along particular directions. This also indicates that in which direction the heat will flow, right? So this, is indicated that you can get this phonon heat was capacity is flowing from top to the bottom, but not to the reverse speed. Okay, you have an assumption. So this method can be applied to many other examples. This is an ongoing unpublished work. We can apply this to ferroelectric insulated interface. In the earliest part, I mentioned that it's a 2D electron gas. This is conducting electron conduct interface. This conducting interface is very interesting. The phonon compared to the conducting interface will be unfair. It's just not metallic material. It's a spectacular refraction. So this means that the two electron gas at this interface form a region which is conductive and also thermally cooled. Okay. So you can also imagine that if you have a two electron 2D material like silicon germanium, silicon and put a piece of graphite with some people in this to be structure. And graphite will maybe keep the interface cooler. I just talked to a few people actually a few weeks ago and who did this kind of study. And still quite very excited with one experiment for a single layer of film between two different inorganic materials. So working hard. All right. I think that is long enough, and I want to summarize today's talk just by saying that with electron microscopy, you can choose a technique that you solve different problems. For example, you can determine atomic scale property, for example, correlation by using quantitative electron microscopy to see a dynamic evolution of microstructure, for example, mutation and growth of variable bodies by institute here. And you can also use a new technique of 4D step, determining local electric field and the charge distribution, and they get much more functionality for local region. Use a newly developed vibrating electron microscopy. You can determine local global transport and also the vibration of lattice or vibration of molecules in the nanoscale. So this can be very powerful. Look in the future. In addition to those continuing developing of new techniques, for example, we are working on a project to try to introduce terahertz laser with a few poles. One is a pumping, another is a delay, and two laser. And then into the microscope, and then put this post laser beam on the sample, and then focused electron beam pass through, and then we can study the interaction between electrons and photons and how this respond to this short pulse of the terahertz laser. And then we can use other techniques to improve the sensitivity and so on. Before I stop, I just mention that the work for charge density mapping and the institute here was done by Chris and Diego, graduate student and postdoc on the paper, and also a student who just graduated a 4-year internship. And then the vibrational microscope mainly driven by two people. One is a postdoc, Qing Xu, another is a Czech graduate student. We have been done excellent work in this field. So the work was supported by the Department of Energy and also partially by the Department of Material Research. Our wonderful collaborators, for example, they are strong and UFO making a very nice interference to us. And Professor Ruchi will provide a selective support for the DFB populations. Thank you very much for your attention.
Oh yes, I'm inactivated from Saban University and as well as the base locally here part-time. So I'm wondering about your charge sensing technology. So I'm just wondering how precise can it be? I'm curious. The reason I'm asking is, for instance, there are cases in topological insulators and so on, in which a vortex or some sort of a localized magnetic field or basic magnetic defect can actually capture a fractional charge. So I'm wondering if you can use your technology to actually integrate over this charge distribution and actually tell that there is a fractional charge rather than integer, not integer. Would that be a possibility, or is it like
that very much? So I guess at this point it's very hard to there's the accuracy and also we estimate the error deviation of the data. I think it's still large, very hard to. It's a very interesting problem. It depends on the further development. If we can further reduce the crop size to currently is to 5.5 angstrom. So further improvement by 50% will significantly improve the accuracy. With the current setting, I don't think we can comfortably say we can distinguish fractional charge. But in the future, it is possible.
You hope to get them.
Yeah.
Yes.
Xiaoqing, wasn't your electron or whole gas model at the interface for the stepwise jumps and domain by domain as domain or motion is annihilated or created? Because that is a really rapid. I don't know if you can catch it, but then
Giving the electron charge distribution as a function of domain motion.
right, you have these electron and whole gases at the
Yeah,
bottom.
yeah.
And at the top, where you actually modify your top, this called electrode and then bottom electrode or substrate. So wouldn't that pose as the domain will move, instead of a smooth motion, a jump like one?
Oh, okay. Okay. So this is not, related to the measurements of the charge, but it's whether or not this interface of charge is a electron gas or whole gas, whether or not this building field at interface influence the motion of the domains, the staging of domains. Yes, it is. So in the details of this PTE switching, business forward switching, I think there's several paper, visual communication, and also PTE, EFO was in science paper. By Chris and Gao from my group, describe several examples. The building potential due to the interface charge will make one type of domain switch motion is impossible. So have a probability hint to what particular direction, and the switching have to be can occur, but at much larger field. It is, and also even defects. You have a planet defect, which is also a charge. There's also have a building field there, and you have a very much stronger healing effect than shown by visualization. Yes, very good question. Yeah, it is significantly influence the switching and the growth of domains. Yes.
From something in your stand. I'm wondering, in this ferroelectric transmission, is there a phase transition between the conversions to other phases? Or is there a small change in the atomic coordinates?
With a mechanism, what is changed in structure when the domain switch? Right?
Yeah.
Yeah. So the contrast you see from contrast between two different domains, you see the middle movie. The contrast is due to the diffraction contrast, because you use the diffraction contrast. Electron diffraction is sensitive to any small change in the crystalline structure. For the bismuth chloride example, the ferroelectric domain wall, it is also ferroelastic. In other words, it's like a twinning structure. For electron beam, have from one domain to another domain, the orientation is changed a little bit. Therefore, the intensity of the electrons will be changed in dark field. But for 180-degree domain wall, we do not have a ferroelasticity, only in like a similar to the interface boundary. But the polar ferroelectric material has a low center symmetry. Therefore, the electron diffraction intensity is different from C or minus C. So that small difference also induce the contrast in the diffraction of image. Okay.
My name is Emergent from TÜBİTAK Marmara Research Center. My question about experimental part actually. I was wondering if there is any special substrate or sample preparation method because I am also working on perovskite materials. We are doing perovskite devices. They buy their, IQ and other electron injection layers and so on and so on. Is it possible to make this kind of imaging directly from those samples?
So what was your just about your material? Your material is you say it's also perovskite.
Correct, I did.
It's like hybrid perovskite for solar cells.
So that's that, yes.
The same technique may be applicable to those being sensitive. The challenge is electron being damaged. So in this material I show you, the oxide is quite stable. So the experiment for 4D stem will cost about an hour to collect all data. For the beam sensitive material, probably only survive for a few seconds or a minute. That is significantly shorter. But there is a very active research right now developing the beam sensitive materials for the stem. Those from Europe and US. So like the diamond sickness, the electron being single results to the UK. And also Irvine, they are leading to develop the body set actually for beam sensitive material that would be available to try. And they also develop the same techniques to protect us. It is challenging problem. I think that you see the development of TM in the last 10 years is so fast. I think we'll solve the problem in the future.
Thank you.
I was going to talk also later during dinner and stuff, so I don't want to explain it for I like.
Apologize for delay.